Thank you very much. Good morning, everybody. Good afternoon, forgive me. As the Director of the United Nations Office for Outer Space Affairs, I'm delighted to be partnering with the Portuguese Space Agency to mark the start of the Conference on Management and Sustainability of Outer Space Activities. And my thanks go to Mr. Hugo André Costa and Portugal Space and his whole team for the kind organization. I will be handing over to Hugo to introduce this conference in just a moment and to highlight why it's so important to you. But first, allow me to say a few words. In May earlier this year, the United Nations Secretary General issued various policy briefs where stronger multilateral cooperation is required. One of them was in the field of space. It is called For All Humanity, the Future of Outer Space Governance. These briefs follow his report on the future of multilateral governance called Our Common Agenda, and discussions on these areas should ultimately drive the creation of a pact for the future as an outcome of the UN Summit of the Future taking place next September in New York. In the policy brief, the Secretary General identified specific space-based challenges where stronger multilateral cooperation is required if we are really going to stand a chance of re-energizing the 2030 agenda and truly harnessing the power of space to achieve the UN Sustainable Development Goals. These challenges include space debris, space traffic, and space resources. This conference puts the policy brief at the center, and it seeks to convene deliberations around these three issues. It comes at a time when, as I'm sure you know, many actors would like to work on space issues, and when the pace of technology advancement risks leaving policymakers behind, when in fact the need to act is upon us right now. There is no better, more informed body to deliberate on these issues besides COPUS, the Committee on the Peaceful Uses of Outer Space. But its deliberations cannot happen in a vacuum. They must be informed by the latest developments happening in industry in a variety of fields. I would like to invite member states to consider the Summit of the Future as an opportunity to put down a marker of its vital role and to share their perspectives on the importance and the future of multilateralism and outer space. With that, I pass the floor to Hugo. Thank you so much.
Thank you very much, Director, and thank you, Arti. And welcome everyone to the first virtual symposium that will focus on these technical aspects of these three core issues. It will be followed by a second virtual symposium later on in March about the policy implications on these three core issues, and we'll conclude in an in-person meeting in Lisbon in May 2024. But why does this matter, and why does an already burdened multilateral system needs to consider these space issues? Because if we do not find the global consensus on these issues, we will not be able to ensure that space data services can play their rightful role in enabling the SDGs. From satellite communications to Earth observation to space science, they are all indispensable to achieve the 2030 agenda and to saving and improving both the planet and the lives of those on it. Right now, these applications are under threat. Without an effective multilateral governance, the benefits of space might be lost for future generations and therefore for the SDGs. The United Nations must advance on outer space governance to ensure that this sector can continue to drive progress on sustainable development. This is the Secretary General's vision behind our common agenda. We invite you to work with us towards a successful conference in Lisbon next year to cement the potential that space has for turbocharging the progress of the 2030 agenda. As one member state, UN member state, I call on fellow member states and other stakeholders across the space ecosystem to push for a stronger multilateralism on space, to pursue space governance with ambition, conviction, for the sake of sustainable development. I would like to remind us all that until the end of the year, the member states should provide written inputs to the Pact of the Future in New York, and verbal informal consultations will happen now in the beginning of December. I would like finally to thank to all for your time, to the moderators, to the rapporteurs and speakers to contribute to this endeavor. We look forward to a constructive and fruitful discussions in the upcoming sessions to help us building the future of space governance together. And with this, I would like to give the floor to the moderator of our first session on space debris, Ms. Andrea Klein-Sassa, from the Federal Ministry Republic of Austria, Climate Action. I would like also to remind those that are attending these sessions that it is being recorded, and if those who want to pose questions, you can find it on the comments on the comment sides on YouTube. And with this, again, thank you all very, very much. And thank you, Andrea, to join as the first moderator for our first session. And I'll now like to give you the floor. Thank you all very much.
Hello? Hello, everybody. Do you hear me? Just give me a signal that you hear me.
Yes, we do.
Thanks a lot. So, hello, thanks a lot. And I'm really pleased that I can start off this first day of considerations on space debris. So, our planet is surrounded by spacecraft that fulfill vital roles. They explore our changing climate, they provide global communications and navigation services, and they answer important scientific questions. However, some of their orbits are very cluttered, and some are increasingly burdened with fast-moving debris from retired satellites and rockets. This threatens our future in space. The 2023 Interconnected Disaster Risk Report even names space debris as one of the 6 interconnected risk tipping points that represents immediate and increasing risks around the world, along with accelerating extinctions, groundwater depletion, mountain glacier submelting, unbearable heat, and uninsurable future. So this is a very serious subject. In our session, we will discuss models and techniques for space debris and orbital debris mitigation. We will hear short 10 minutes input of 4 panelists, and then we will have some time for questions and discussion on possible effective solutions. I would like to thank also the rapporteur of the session, Maximilian Bethmann from the German Space Agency at DLR for the joint preparation of the session. So I would like to call the first speaker of our panel, Ralf Dinsley. You can open the camera, and I would like to briefly introduce you. Ralf, hello, is founder and managing director of Northumbria Limited, and he's a recognized specialist in space surveillance and space situational awareness. Previously, he has been working at the Royal Air Force, where he was leading the UK Ministry of Defence operational contribution to global SSA, supporting 3 significant programs. In 2017, he created Northern Space and Security Limited, the UK's only commercial SSA company at the time, and he brings in the private sector perspective into our discussions. Ralf, the floor is yours.
Thank you very much, Andrea. Good afternoon, everybody. And I'd like to start by thanking the organisers for inviting me to participate in this event, and to thank them for the opportunity to discuss and to contribute to a subject close to my heart. I shall try and share my presentation. And hopefully you can see that now. As explained by Andrea, I am Ralf Dinsley, the founder and managing director of a new company known as 3S Northumbria Limited. It is a newly created commercial company based in the northeast of England and dedicated to ensuring the long-term sustainability of the benefits from space. Our mission is to create sustainable space solutions grounded in the principles of a circular economy for space and evidenced through assured space situational awareness. I began my career as an air defence specialist in the Royal Air Force almost 40 years ago. And for the last 25 years, I have been working within space situational awareness in both the military, civil, and commercial space sectors. As a military space surveillance practitioner, I have personally witnessed the tracking after effects of the 2009 Iridium Cosmos collision, whilst we were still dealing with the ASAT event of 2007. And did you know it took almost 2 years to catalogue all the trackable objects from the 2009 Iridium Cosmos collision? But consider what happened to those pieces we could not track. Over the last 2.5 decades, I have watched the discussion escalate around a space debris apocalypse, and yet the sky has still not fallen in. I know we cannot become complacent yet. We must learn to better highlight the problems and solutions for orbital debris, whilst considering the implications both on the orbital environment of today and sustain its benefits for the future. There is no question that we are not going to stop using space. In fact, over time, we'll be using space more and more. I spent 16 of my last 18 years of the Royal Air Force as a space tracking practitioner and developing space situational awareness solutions for future military deployment. Upon retirement from the Royal Air Force, I created the commercial company known as Northern Space and Security Limited, became known as NORSE, which in just 5 years became the UK's lead dedicated orbital analyst developer. And that term developer, I believe, is key. The company was acquired by Raytheon UK in 2022, and I've recently begun what I class as my third retirement project in creating 3S Northumbria. The driving factor behind NORSE and 3S Northumbria is that I know government career profiles do not support the depth of experience most needed for space situational awareness. Often moving personnel on or after only 2 years for broadening, the most important thing we can do is to continue developing space situational awareness expertise. SSA practitioners are essential for the sustainability of our orbits. The task may be expensive, but most significantly, it takes experience to do it correctly. And that takes time. To be honest, at least a decade to really become experienced. Even after 25 years, I would not say I'm an expert. I'm experienced, but I learn something new every day. The biggest problem we currently face in relation to debris, both tracking and characterization of debris, is our historic dependence on space surveillance and tracking mechanisms, grounded in military operations and doctrine, and the lack of investment in dedicated tracking systems. The military are focused correctly on security, and therefore their funding is dedicated to this, and often safety and sustainability become a spectator. It is time for civil and commercial space to take control of the situation. We need far more data than the current disparate sources can provide us, and we need that to be near persistent data, particularly for LEO. Current operations rely too heavily on systems optimized for different missions, but employed to support space surveillance and tracking. Within the military, the vast number of radars for LEO tracking are optimized for missile warning. Academic systems have been appropriated from weather monitoring or adapted from other science missions to support space surveillance and tracking. We keep on talking that space situational awareness is essential, and yet we never or rarely dedicate funding for specific optimized systems. I believe by taking the responsibility as a civil mission, we can allow the military to focus on security, and the civil systems can take care of the sustainability and safety of space. Over the last 10 to 15 years, we've seen a growth in commercial SSA. And one thing my experience has shown me is that commercial space is more agile and able to move quicker than government-funded space projects. They can pivot to the need of the customer. Currently, the establishments appear reluctant to fund these commercial ventures. Like I say before, SSA is expensive, but it is essential. Can we afford not to buy into the developing commercial capabilities? Companies such as Exanalytic Solutions have developed a capability for tracking objects above 8,000 kilometers near persistently from the ground. Their observatory footprint has reduced the sun exclusion to less than 6 hours in many instances, and that same footprint has negated the effects of weather, such as cloud cover. With more than a decade of operations, they own a rich, accurate database and provide both data and support to governments and commercial operators alike. They see more activity on orbit far quicker than government capabilities, and have reported to both the UN and their own government on non-traditional behaviours that have been occurring in GEO in recent years. The situation for LEO is a little more difficult, as traditionally radars have been employed tracking objects in this regime, and radars are very expensive to both build and operate. The US Space Surveillance Network has a network of radars, until recently all in the Northern Hemisphere, which are mostly optimized for missile warning and prioritize security missions for tracking over catalog maintenance. Therefore, some objects may only be tracked once every few weeks, or less, within every 28 days. Commercially, LEO labs have begun deploying a network of radars, and as they are dedicated space surveillance radars, they are optimized for tracking orbital objects. They can track objects way smaller than the US Space Surveillance Network. But then the difficulty lies in classifying and correlating these smaller objects, especially if they're not observed on a regular basis. Persistence is key. How useful can they be for safety if all they are doing is providing uncorroborated information? Does it not clutter up the picture? As they track more objects, it becomes more expensive. Can we afford not to pay for this? And where are the customers for this? But we can operate in other ways. We've always used radars for LEO. Why do we need to focus in radar? Raytheon North UK have developed or are championing a relatively simple camera network designed to track larger objects in LEO a lot more cost effectively. Hundreds can be deployed globally, reducing the effects of sun exclusion and cloud, and providing near persistent tracking of objects in both LEO and beyond. Early trials in the northeast of England produced a rich database of information, objects as far out as high MEO orbits. Using light streak for basic cataloguing information and light curve analysis for object characterization. By deploying the cameras globally, we can create a near persistent surveillance fence on objects in LEO, collecting data numerous times per orbit cost effectively, and releasing the radars to focus on more difficult, smaller objects. What I'm saying is we have a different mindset, a different thought process of how we do business instead of we've always done it that way. Basically, the civil camera system can take care of the background noise for object cataloguing, whilst the radars track the smaller items and the military take care of security. A little like the way we manage air traffic presently. In conclusion, what I'm saying is that we should be focusing on gathering real data, challenging the two paradigms of the military have this covered, and we've always done it this way, and developing deep expertise in order to ensure the future sustainability of our orbits and retain the long-term benefits we receive from space. Modelling and simulation have their place, but until we have a rich space surveillance data ecosystem, we will remain in the dark. Thank you very much.
Thanks a lot, Ralph. As I said, we will take all four panelists in a row, and then we will discuss. The next speaker I would like to call is David Zamora from Eutelsat. He steps in for a female colleague who couldn't come. Eutelsat is one of the world's leading satellite operators with a powerful fleet of satellites serving users around the world. David, the floor is yours.
Hello, good afternoon. Can you hear me?
Yes, we can.
Okay, excellent. Thank you. So, good afternoon, everyone. So, first of all, I would like to thank the organization to give me the opportunity to share with you Eutelsat experience regarding end-of-life operations. You may know that Eutelsat Group is the combination of Eutelsat and OneWeb with a fleet of 36 geostationary satellites and a low Earth orbit constellation of more than 600 satellites. But today I will focus on the GEO regime, although some of this experience could be extrapolated to other orbital regimes. The way we have approached space debris mitigation at EUTELSAT have changed through years. Before 2005, EUTELSAT was acting as a responsible operator. This means the satellite were controlled within their designated orbit control windows. Orbit relocations were guaranteeing not entering into the station keeping box of other satellites, were avoiding minimizing debris generation during nominal operations, were allocating 3 sigma propellant for reorbitation in line with international recommendations, and at end of life, passivation, satellites were passivated after reorbitation. A space debris policy was put in place in 2005 in order to respond to the requirements from the FCC to support our US clients and from our ISO 9001 certification in operations, to set a common baseline for our decommissioning activities and to establish a process to improve our end-of-life disposal operations. This space debris policy is updated on a regular basis, and it is fed with international guidelines and recommendations, the French Space Operations Act, which entered into force on the 10th of December 2010, and of course, the return of experience. The EUTELSAT space debris policy covers all phases from satellite separation from launcher till satellite decommissioning, aiming at the long-term sustainability of space operations. The general principles of this policy are avoiding limiting the amount of debris released in a planned manner, minimizing the probability of the satellites becoming a source of debris, controlling the satellite within their allocated orbital control windows by standard routine periodic orbit correction maneuvers, avoidance of radio frequency interferences, of course, allocation of 3 sigma propellant budget for reorbitation to 300 kilometers above the geo height, and passivate the satellite at the end of the life. If we focus on end-of-life operations, the main principles to be followed are, of course, raising the orbit to a graveyard orbit to keep the spacecraft beyond the geoprotected region. This is geo height plus minus 200 kilometers in the long term, without entering into the station keeping box of other satellites. This implies allocating propellant to raise the orbit by 300 kilometers, but this might not be enough. So we need to make sure that this is 300 kilometers are above the minimum perigee height computed using the IADC formula. We need to manage close approaches during end-of-life operations. We need to manage radio frequency interference with active satellites during these operations. And of course, we need to complete fluidic and electric passivation before satellite switch off. So far, 25 of our satellites from 7 different platforms have reached their end of life, including 1 spinner and 1 full electric satellite. The first reorbitation was completed in November 1993 by ESA on behalf of EUTELSAT, and in November 2003, we have completed our first reorbitation from our headquarters. In January 2018, we are completing the reorbitation of a spinner satellite, and less than 1 month later, we have completed the reorbitation of our first electric proper satellite. We continue with reorbitation, and the last reorbitation was completed in July 2023. All these reorbitations, we've learned many things, and I would like to share with you some of what we have learned, of our lessons learned. First of all, and probably one of the most important one, is that a reorbitation plan shall be prepared in advance. This reorbitation plan shall take into account all ground system and satellite constraints, including the management of radio frequency interferences. We should improve the computation of the terms to be considered to compute the minimal altitude required to ensure that the spacecraft will remain outside the geoprotected area and the altitude stability. This is the cross-section to mass ratio should be 60% of the cross-section to mass ratio of the control spacecraft at end of life. We should complete the end of life operations while in TCR station visibility in order to guarantee that we have commanding capability. Nevertheless, it is also important to secure electric passivation to ensure correct spacecraft switch off in case of unexpected loss of telemetry and telecommand links. It is also very important during the operations to keep up-to-date owner-operator ephemeris, including the effect of future maneuvers for close approach management. In the past, during one of the reorbitations, we need to manage a close approach that was a bit It was not triggered by all the SSA data providers. It was only triggered by the Space Data Association because it was a close approach between our satellite, which was performing maneuvers, reorbitation maneuvers, and another satellite that was performing a relocation, an active satellite. So this is very difficult. This, unless we use owner-operator ephemeris, is not possible to catch these kind of close approaches. It is also very important to minimize orbit perturbation during fluidic passivations. Once we have raised the orbit to 300 kilometers or above, we cannot forget about the orbit. It is very important that during the fluidic passivation, we put in place a strategy that is minimizing the perturbations to the orbit. Otherwise, we risk to have a period that is lower than 300 kilometers and not being able to ensure that the satellite will not re-enter in the geoprotected area. We have also patented during this reorbitation a method for reorbiting maneuvers, for reorbit operations in the absence of combustions. And we have also developed a method for emergency reorbitation. This is reorbiting the satellite in a short arc in less than 12 hours. Thanks to our long and successful experience in geosatellite decommissioning, we can conclude that it is extremely important to prepare a reorbitation plan specific to the mission, but incorporating applicable lessons learned experience from previous reorbitations, even if they are not specific to that mission. The close approach and RF management needs to be taken into account in the reorbitation plan and during the operations. The preparation, technical expertise, and close cooperation among teams and satellite manufacturers are key factors for the success of the end-of-life operations. And finally, the success of satellite end-of-life operations is of paramount importance for the long-term sustainability of space operations. Thank you.
Thank you very much, David. And I would like to call now the third speaker of our panel, Michael Steindorfer. He holds a PhD in physics. Hello. Topics nanotechnology, nano-optics, 3D laser lithography, and biomimetics. He has been working at the Space Research Institute of the Austrian Academy of Sciences since 2015. And since 2022, he has been group leader for satellite laser ranging. Michael, you have the floor.
Yeah, thank you. I hope you can see my screen and also can hear me well.
Yeah, perfect.
Perfect, thank you. Yeah, thanks for the kind introduction. I'm happy that I can give a little introduction about space debris laser ranging and technical and scientific applications to that. So yeah, I said before, I want to introduce laser ranging in general, and this I wanted to do as compared to satellite laser ranging, comparing satellite laser ranging and space debris laser ranging to each other. So basically here on the right side, you see how it looks like if during the night time we track a LEO satellite pass with our laser at SLR station Graz Lisbon. So this is really also the view you have when you're walking around our station. So basically, what is laser ranging? Laser ranging is laser-based time-of-flight measurement in principle. So what you're doing is you're firing a laser beam to a satellite and then detect its reflection. And during that, you have to do some high-precision timing. High precision is meant that it leads to up to millimeter precision range measurements. So basically, what is done is you detect the start epoch of a laser pulse and the arrival epoch, and then the rest in principle is relatively simple by just calculating the range with a product of time difference times speed of light. So in Graz, we have different approaches. So first of all, we are having a satellite laser ranging laser, which is in the order of 0.8 watt, 2 kilohertz, meaning 2000 pulses per second. Operating at 10 picosecond. And then for space debris laser ranging, in contrast, you need a little more power, meaning 16 watts, only at 200 hertz, 200 pulses per second with 3 nanoseconds pulse duration. So in comparison to that, the future, in our opinion, is combining both techniques, high power and high repetition rate, with the potential to do both things at the same time, satellite laser ranging and space debris laser ranging. So yeah, basically about the targets. Targets for satellite laser ranging are satellites which can be in orbital regimes up to 36,000 kilometers, geostationary orbits. For space debris laser ranging, we are actually limited to distances up to in the order of 1,500 kilometers, maybe 2,000 kilometers range. As you see on the right side, there are various different satellites tracked with satellite laser ranging, but all of them rely on retroreflectors, which are mounted on these satellites in different arrangements. So there are, for example, spherical satellites like the geodetic satellites, and also for Galileo, as an example, there are just panels mounted with up to 80 different corner cube retroreflectors on there. So this is basically the main difference between satellite and space debris laser ranging. We are having here the reflection principle. So in general, you're using retroreflectors for satellite laser ranging, and for space debris laser ranging, basically the whole target reflects the light and then distributes the photons, for example, across Europe in our case. For different, let's say, famous space debris laser ranging targets are, for example, TOPEX, JASON-2, or also we are tracking different upper stage rocket bodies, for example. So I want to introduce laser ranging based on our observed minus calculated residuals. So this is basically how a data set looks like. A lot of points. At some places in the data points within the noise, there are denser parts. And yeah, I will just explain on these range deviations from the predicted reference orbit. We call it observed minus calculated residuals, on how space debris laser ranging or space debris measurements can contribute in a very unique way. So basically, you can see returns from the object, in this case Envisat, which are denser in this graphs, which correlate to returns to reflections at almost equal range measured range distances. So explaining a little further, because this example is somehow special, you can see that in the range residuals, in the deviations from the predictions, there are 3 different regions to be found. So at first you can see this region marked in red with very small deviations, and then you see here the green little region, upper region here, and then a central region here. And I will explain a little bit in further detail where this different information is coming from. So first of all, the first part, this is actually coming from the retroreflectors from Envisat and from the target Envisat here. So on the very bottom of the satellite, which is actually inactive and rotating, you see these retroreflectors which are mounted. So they are giving a signal which is not really distributed in a wide range. Then the second part you see here, there are reflections coming from the whole body. As the satellite is rotating, the whole body reflects photons, which we are firing on the laser, and hence you see a distribution of the body ranging from approximately 6 meters here. And then also you can see a reflection from a third part, which is the solar panel. So as you see here, the range deviations, they already span up to 20 meters, which is correlating to the whole size of the target Envisat. So this is giving a short introduction about space debris laser ranging in general and how the contribution is. What we also can see is that the target is rotating. So actually the deviations between the range residuals, they are reduced and increased with the rotation period. You can see here that approximately 190 seconds is the rotation period needed for one rotation of the satellite Envisat. A further contribution we want to highlight is multistatic laser ranging. This was a very interesting experiment we did with a couple of different stations contributed across Europe. So basically, the main idea is that one station is firing photons with a space debris laser to a certain space debris target, and then as the photons are distributed across Europe, different stations can step in even without having a laser by themselves, and measure the reflections. So this can really be used to increase the orbit prediction quality a lot. On the right side, you see an example of simultaneously Graz detecting their own photons and then Potsdam detecting Graz photons at the same time. Another interesting thing is if you combine space debris laser ranging measurements with light curves. So this is what you basically see below here. In green, space debris laser ranging residuals, as you saw before, leading to a spread of approximately 13 meters in range. And also there is a rotation in the targets. So these ups and downs in the residuals, you see these are actually correlating to a rotation period in the order of 120 seconds. What you also can see is single photon light curve, which was recorded here. So light curve is corresponding to the reflection of sunlight of the target itself. So these ups and downs you see here, they are very, very well correlated to the range residuals you found. And they also give an indication on the reflections of the different surfaces of the target. In this case, a rocket body, which was measured here. Yep. Just to give you a summary and outlook, and in what we believe are future topics. So it's very, very important to say that for reliable space debris laser ranging, more stations are needed. So it has to be realized that there are either existing stations upgraded or new stations are built with that capabilities. And besides that, it is also important to improve existing observation capabilities to increase the time the stations can operate. Then, as we also mentioned before, we see megahertz laser ranging as a real technique for the future. So you will only have one setup to be used for satellite and space debris laser ranging. Then, as already mentioned, data fusion is quite important. So different techniques synergizing to get improved data analysis capabilities. And what we also see is for amateur astronomers, maybe they can also play a part in the future, maybe not for satellite laser ranging or space debris laser ranging, but for telescope observations looking at space debris targets. So this is basically the input from my side. Thank you.
Thank you very much, Michael. And I would like to call on Thomas Schildknecht. Professor Dr. Thomas Schildknecht is the director of the Swiss Optical Ground Station and Geodynamics Observatory Zimmerwald and vice director of the Astronomical Institute of the University of Bern, Switzerland. He is a distinguished expert on space debris, space safety, and sustainability, and serves in numerous international technical and policy committees, amongst others, Interagency Space Debris Coordination Committee, IADC, where he had led negotiations on the IADC Space Debris Mitigation Guidelines, US-Russian space surveillance workshops, and many more. And he's also a member of the Swiss delegation at the United Nations Committee on the Peaceful Uses of Outer Space since 2011, where he substantially contributed to the work of its working group on long-term sustainability of outer space activities. Thomas, you have the floor.
Thank you very much, Andrea. First of all, I would really like to thank the organizer for having invited me here to this workshop and being able to share my considerations concerning sustainable use of outer space. I hope that you can see my presentation.
Yes, perfect.
Okay, thank you. I have been involved in and working in the domain of space debris, and in particular space debris observations, for almost 30 years now. Mostly on the passive optical side, but also recently on the laser ranging observations. So observing and characterizing space debris and the space debris environment is absolutely foundational for safe and sustainable use of outer space. And I'm going to try to show you a few examples. So first of all, we know all this picture here. The question is really, what do we know? And we know about 35,000 objects. I will call them by name. Usually, this is the catalog of orbits of objects which we follow up more or less on a regular basis. But this is only the tip of the iceberg, as we know. There is more than, depending on the model, 900,000 or 1 million objects larger than 1 centimeter. And just to keep in mind, if you collide with one of these pieces of 1 centimeter, the energy of a hand grenade is going to be released. So these are lethal objects if you collide with them, and they're not tracked. They're not trackable right now. So, as I mentioned, the 1 meter pieces, we know all of them in low Earth orbit. We know most of them, I would say, in higher altitude orbits up to GEO. 10 centimeters. Our catalogs are not complete, even at low Earth orbit for 10 centimeter size objects, even less so at altitudes like the MEO, medium Earth orbits, where our navigation satellites operate, or in GEO, where we have very important assets as well. 1 centimeter, as I mentioned, we are talking here about 1 million objects. For sure, we don't know any of them really. So we have a huge knowledge gap there. 1 millimeter, this is not lethal anymore, but it can degenerate your assets. You lose power on your solar rays, you can have a degeneration of your optical instruments, and so on and so forth. So let me show you why data is foundational for all the discussion about safe and sustainable use of outer space, and in particular also to the question, what is the most efficient measures to mitigate space debris and to remediate space debris. On the left-hand side here, you see a snapshot of the, let's say, open catalog of orbits. This catalog here includes everything down to 10 centimeters in LEO, and as I mentioned, in higher altitudes, the limit is rather like a half a meter in GEO. Is this the full truth? This is the same catalog, but superimposed in green. What you see is results from surveys we have been doing together with our scientific colleagues all over the world, and in particular in Russia. More than 1,500 fragments here from 3 breakups. You see the 3 breakup events here, the orbital planes or the orbits of these 3 parent bodies. None of these 1,500 plus fragments shows up in the official catalog, and most of them do not show up even today, 4 years after the event. So no single data information source is providing you the full truth. This is a really important fact that you will have to get all sources, all data you can to complete your picture. So this movie here shows you a series of images we took 12 hours after the breakup at our own observatory in Switzerland. The streaks are stars which are streaking by, but I don't know if you see the dozens of small points all over here. It's like salt and pepper on these images, dozens of fragments which stem from that single breakup. So you have to look for them. They don't show up in the catalog like this. So I mean, we are concerned currently mostly about, let's say, low Earth orbit, medium Earth orbit, a little bit about GEO. I mean, one of our presenters mentioned in particular GEO and what we are doing there, or what they are doing there in terms of mitigation measures. We all want to go back to the moon. Are we ready for the moon? Are we ready for a safe and sustainable operation in the cislunar domain or in the domain in between, let's say, Earth and the moon? I would say not at all. We have not even, come up with all the ideas how we would do that, how we would make sure that we have a catalog of whatever type of objects up there. So this is going to be an absolutely, completely new challenge to be tackled soon. So space safety and sustainability. As I mentioned, the basic information comes from surveillance and tracking. So we need to discover objects and events. We need to regularly track them. We also need to physically characterize them. It's not just about knowing where they are, it's also knowing about what they are, not so much for space safety, but in particular for the long-term sustainable use, because we need to know if a piece or an object we have been seeing is whatever, a piece of metal, is it a piece of solar array, is it a piece of multi-layer insulation, because that will allow us then to conceive, let's say, efficient mitigation measures. And for sure, we have to characterize the lethal and non-trackable population in order to come up with risk assessment for our missions. In terms of the space debris environment, and I call this space debris environment management, we need to assess and monitor the debris environment. We absolutely need statistical population models and evolution models. Once again, if you're going to talk about mitigation and even more so, remediation measures and their efficiencies, or about regulations, or about guidelines and their efficiencies, we all rate them versus our evolution models and statistical population models. We want to know, okay, if we take that measure, it will make a change in the space debris environment in 10 years, 20 years from now in this manner. And we want to rate these measures to come up with the most efficient ones. Yes, we need mitigation rules. Again, these rules need to be rated against evolution models. We need post-mission disposal, as already mentioned by one of my colleagues today in the GEO region, where we have a good adherence to the current rules. We need post-mission disposal, particularly in GEO. All this discussion about the 25 years disposal after the end of the mission. Should we reduce that to 5 years, 1 year? We need to do collision avoidance. So most of the assets up there do not have collision avoidance capability in terms of numbers. All the small size CubeSat satellites do not have that. Do we require collision avoidance capability for all objects above 400 kilometers? We are talking about active debris removal. We're not so much talking about just-in-time collision avoidance. What do I mean with that? Most of the objects out there are not maneuverable. They're space debris left over from, 60 years of, almost 60 years, most of them of activities in space. We have large epistages. We have Envisat up there. If two of them are on a collision course, the only thing we can do today is, watch the show. Nothing else. So we need means to prevent collisions between non-maneuverable objects, which means we need just-in-time collision avoidance means. And finally, we all talk about space traffic coordination. This is really the day-to-day task for the operational part of the population. So we maintain catalog, we assess and propagate uncertainties, we issue safety messages, we manage the orbit capacity, we communicate and verify standards and best practices. And of course, we need rules of the road, norms of behavior, standards and best practices. Why do we care? And again, this is going to give us the boundary conditions for the discussions today. We care on one hand because we are spacecraft owner and operators, the safety of flight. We want to prevent collisions. So we need traffic management, collision avoidance maneuvers. If something happens, we want to know what's the cause, what's the reason for my contingency. While, if you're a government, a space agency, or a scientist, you care about protecting our vital space services, critical infrastructure for the societies. But we also care about the long-term sustainable use of space. And, of course, that goes together. We need to have models about the evolution of the environment. So we should really be aware that there is no trade-off between, let's say, traffic management versus environment management. And most of the focus today is on traffic management, collision avoidance. And we absolutely need to do that. I mean, that's the first line of defense. But we also need environment management. What does this mean? It means, for example, that we need to be aware that the long-term evolution of the space debris environment is driven by collisions of massive, non-maneuverable objects. And there we need to come up with techniques to prevent that, being it ADR or just-in-time collision avoidance. So my take-home messages: scientific research and in particular observations, they provide the foundation for sustainable use of outer space. And this knowledge forms the basis against which the efficiency of the current implementation of the guidelines, but also the rationale for new recommendations, needs to be rated. And with that, I thank you for your time.
Thank you very much, Thomas. I would like to invite all the panelists to switch on their mic and their camera. I would like to say that this input demonstrates why these workshops and symposia are so important. We have here an interdisciplinary and input from various sectors also, and this really demonstrates that this dialogue and this interchange is so interaction is so important. While you are all here now on the podium, on the virtual podium, I would like to start off with a more general question, and then we will have questions more digging into the topics of our session. So my general question, whomever wants to start off, is: what do you believe is the single most important element to be included in any future regime or governance framework on sustainability in space? Who wants to take off? Of course, given your perspective, technical perspective. Who wants to take off? Ralf, maybe.
I think Thomas had a hand up there, sorry.
Okay.
Thanks. Yes. From my point of view, the most important, and we have it in all our guidelines, the most important is actually to make sure that we take out of the environment everything we bring up. We call it post-mission disposal, whatever, but we should not leave a trace. up there. And this is the most efficient measure we all know. Of course, it's not tackling the heritage. It's not tackling what's up there already. But it's absolutely clear with the current traffic and ongoing traffic, which is increasing almost exponentially, it's the most important thing to do. Don't leave anything up there. And the problem is we have the guidelines, but we don't have the incentives right now or any other measures to make sure that we are compliant with these guidelines and the regulations which are there in some of the member states.
I fully agree with what Thomas said, and disposal is going to be an interesting one, particularly as we discover for LEO whether or not there's any problems with polluting the upper atmosphere with all these objects re-entering. And I know Easter have got some workshops coming up on that in the future. But personally, I think the most significant element we should invest in for the future of this is to ensure that we have international capabilities to be able to support object tracking, safety predictions, etc., and international standards across the board, because there are still an awful lot of different systems with different levels of accuracy, etc. The most important bit is to make sure that we get the information, the right information on the right objects, and are they able to do that disposal in the future.
David.
Yeah, I want to join on that. Like, thinking that working together is most important. I mean, there are different groups worldwide sharing different technologies. It's very important to share the knowledge, to share their findings with each other, and to work together while classifying, measuring different targets. So each station, each nation working for like individually, it will not bring the same outcome as if a global effort is reached, tracking a global problem. Let's call it this way.
David?
Yes, so I agree with what has been said. In fact, basically my presentation was about successful end-of-life operations. So I concur with the fact that we should put a lot of effort into the success of the end-of-life operations, and of course we also need to keep to improve the tracking of the objects, as he has been mentioned before. There are many objects that are not currently being tracked, or they are not in the catalog. So this kind of object we should put some effort also to track those objects.
No, thank you very much. One of our topics was orbit mitigation, of our session topics. And I'd like to discuss now a little bit what is required to stabilize the space debris environment up there. So do we need to revise IADC debris mitigation guidelines, or will there an efficient space traffic management system be sufficient to ensure that long-term sustainability of the environment? So what is, to your mind, needed to stabilize the space debris environment?
I would say personally more effective tracking and cataloguing of the information in the first place. As Thomas so well pointed out in his presentation, there appears to be an awful lot of objects that aren't catalogued. So until we actually have a full understanding of even the trackable size pieces of debris, let alone those we can't see, the ones we model, we won't be able to take the right step forward. So an effective collaboration on actually cataloguing all those objects that are up there. We don't necessarily need to know what the active satellites are doing. We just need to know they're there and they can be accounted for.
I would say I agree with this for sure. We need better cataloging, we need better tracking, but to stabilize the environment in the long term, I think tracking alone is absolutely important, but we cannot rely on the fact that we can move all these objects. So we need more investment into technologies, how we move passive objects, because as I mentioned, two large objects colliding up there, I mean, that's a huge mess as a result. We'll have a huge mess. We are talking about a mess which is much bigger than the events we have seen in the past. For example, the Iridium Cosmos. So I think we need means to prevent that just in time. And this means we need the perfect catalog. We need the catalogs which are good to 10 meters in the orbit, so that we can move one of these pieces just by a few meters with whatever technique, pushing it a little bit with laser or any other techniques. But I think for the long-term sustainability, we need to invest more into these techniques. Active debris removal is only one, and we will never be able to remove the hundreds of upper stages we're up there. We are talking about many hundreds, and one mission, even if it's 10 million only, it's too costly to remove all of that. So I think it's the same. I'm calling for, the perfect tracking system on one hand, very good orbits, but on the other hand, on new techniques to be prepared to prevent collisions among passive objects. This is long term. I know this is not what the operator today is much interested in, because he wants just to be safe with his mission, and that's a slightly different priority.
I see David and Ralph again. First, Ralph was first, I see, and then David.
Yeah, I just wanted to, I think Thomas put up a very good point, so I just wanted to underscore that when he said about more effective tracking systems. For far too long now, we have relied on the militaries to say, don't worry, we've got this problem covered. And we may have had an adequate catalogue up to about 2019, but certainly since we started the fast increase in deployment of satellites through things like the SpaceX launches, etc., we've never had an adequate catalogue since then. So we certainly need to invest in systems that better support the cataloguing. And it's a two-pronged approach. So we need the basics for space surveillance and tracking to support it, and then we need the investment into the long-term research to make it better as well.
Thank you, David.
Yes, so I think also something, yes, it has been said, not a single factor is going to help for the long-term sustainability, but I think one of the most important ones could be the post-mission disposal success rate. There are many studies that said that they need to be significantly improved in order to stabilize the population. So yeah, we cannot forget about that. And something that is not mentioned in many places, but I think it's important to educate satellite operators about the importance of the post-mission disposal and of their operations, because not everyone is aware of the consequences of not fulfilling all these international recommendations, following them, etc. Of course, they need to also to be updated, as you have mentioned before. Some of them, they are not adapted to the new space, and they will need to be adapted. And something that it might be a bit harder is we'll need a regulatory framework, because otherwise it's very hard to have everyone pushing in the same direction. I mean, we need to have harmonized rules and a regulatory framework to make sure this is happening.
Thank you, David. And I have seen Michael.
Yeah, and another aspect, which is also like, I agree with all of the other speakers in that respect. That tracking is really important, and also increasing the catalog. But for the existing targets, it is also important, also with respect to removal missions which are coming up in the future, to know what these targets are doing, how they are behaving, how they are rotating. Just know their orientation in space to be prepared to guide such removal missions in the future as well.
Thank you, Michael. And I guess we have some more minutes, as we started a little bit left, to answer a last block of questions on models. What are the gaps of current space debris models? Do we know the main drivers and actual risks for safe operations? What are the gaps of the evolution models? And is there a maximum capacity for orbital regions to ensure safe and sustainable operations? So who wants to to start with this last round of questions?
I suppose I'll pick up on the modelling and simulation piece, and it links back to what both Thomas and I talked about, the need for better data, more accurate data, because the models and simulation are only based on the data information we receive now. And even in recent years, I've heard of organisations trying to apply machine learning to TLEs, which quite scares me, because some of the truth factor in those TLEs is so outdated. It's more harm than it is good. So the most important piece for me is data. And I think also looping back to some of the previous discussion as well, a greater framework is a great idea, but the most important thing is an organisation to be able to enforce that. The regulatory framework needs enforcement. The space law, in my view, is adequate. We just don't enforce it. We've seen a recent event in Geo where a company was fined a mere $50,000 for failing to put their object into the graveyard, and that is not, in my view, of enforcement of rule or regulation. That's just, to them, it's just the cost of doing business. It should have been far higher than that.
Any more views?
I could just add that I fully agree with you. We need more input data, because these models are essentially driven by the input data. It's not so much the algorithms which are used. And, apart from let's say the observations, and especially the small size population, which is a huge gap, I think we also have gaps in terms of the what we call the traffic model. We are talking about 400,000 plus filings for licenses. Is 10% going to be realized? Is it 5%? Is it 50%? And that makes a huge difference in the huge population. My point is that with the current technical capabilities, the technical capabilities for tracking, for collision avoidance, and so on and so forth, there is going to be an upper limit in the capacity, let's say, for whatever orbital shell you're looking at. It's like on a railway track, with the current technical means, we have a limit. We cannot run more than one train every 500 meters or 1 kilometer or whatever. And it's the same up in space. And I'm afraid we have not even been touching that question, because we are here in the UN workshop, and we are all free to use space. We are all free to put up there hundreds and thousands of objects, but we have to be aware as a humanity, as a whole, that perhaps there are limits. There's capacity limits. I don't want to go into the technical details, but just the fact that there could be limits is a huge challenge for the international community.
Yes, thank you, Thomas. This is thought-provoking. Any more inputs? I don't see hands up. This is the last call for, if you want to say something, then this is it. This is the moment. I don't see hands up. So this concludes our session on space debris, models and technique for space debris and orbital debris mitigation. Thank you very much for all your input and all the material you put on the table, where we will then draft our report. And this is a starting point for our journey towards the Summit of the Future and possible recommendations on further developing space and how we use it. And of course, we will continue to work together to keep space sustainable, stable, and safe. And with this, I conclude this session. Thanks a lot once again, and I hand back to Hugo. Thank you very much.
Thank you very much, Andre. Thank you very much to all of our speakers and also to our rapporteur, Maximilian Bettman. We will return in approximately 1 hour at 2 p.m. UTC on a session focused on active debris removal and in-orbit servicing. So we see you in an hour. Thank you very much.